Welcome to this explainer. We completely take it for granted. You pull a rectangular piece of glass out of your pocket, tap a name, and literally within seconds, you are talking to someone halfway across the globe. But the actual engineering required to make that seamless connection happen, it is nothing short of miraculous. So today we're going to decode that invisible infrastructure and break down the digital magic that makes your mobile phone work.
So, what actually happens behind the scenes when you press call? Let's dive right in and demystify the incredibly complex web of towers, databases, and switching centers that connect us instantly. We're going to look at how your phone establishes a connection, how the network tracks you without losing you, and how it routes voice traffic in a matter of milliseconds.
Here is our roadmap for the explainer. We'll start by looking at the two different phone numbers your device actually uses, then move into how you catch a cell signal, peek inside the switching center, break down the step-by-step call routing, and finally, look at the absolute magic of handoffs.
All right, Section 1. The two phone numbers, public addresses, and secret identities.
To really understand mobile networks, we first need to get one thing straight. Your phone actually relies on two completely different numbers to function. You've got your public dial-in number, known as the MSDN. When a friend wants to call you, they dial this. It's basically your public mailing address. But the network doesn't actually route the call using that public identifier. Behind the scenes, the network uses your IMSI, the International Mobile Subscriber Identity. This is a permanent, highly secret number burned directly into your SIM card. Think of it like your social security number. You can change your public phone number as much as you want, but your IMSI remains constant for that specific SIM, and the network relies on it to securely authenticate who you are.
And get this, to keep global communication standardized, international telecom rules dictate that your public phone number is strictly capped at a maximum of 15 digits globally.
Now, those 15 digits aren't just a random string of numbers, they're built using a strict hierarchy. First, you have the country code, which obviously identifies your geographical region. Then comes the national destination code, and this identifies the specific mobile network operator you're using. Finally, you have the subscriber number, which is uniquely yours within that network. It's like a giant funnel. This structured format is what allows international routing to figure out exactly which network operator on the planet to contact when a call is placed.
Okay, Section 2. Catching the cell signal, connecting to the radio network.
So, when you power your phone on in the physical world, it doesn't instantly talk to the main network brain. First, it has to negotiate a radio channel with the BSS, or base station subsystem. This is the hardware you actually see out in the real world. It consists of the base transceiver station, those giant antennas on the towers, and a base station controller, which manages a whole cluster of those antennas. This subsystem provides the absolutely vital radio link between the open airwaves and the wired core network. Literally before you can even pull up your keypad to dial a number, your device is incredibly busy. The second you turn it on, the phone scans for the strongest reverse control channel signal from nearby antennas. It's essentially looking for a dedicated hello frequency. Once it locks on, it passively listens to a broadcast from the tower, specifically waiting for a location area ID. If this ID is new, meaning you've moved since you last checked in, the phone actively requests a radio resource allocation from the BSS. It is silently registering its physical location with the nearest tower so the network knows, generally speaking, where to find you.
Moving right along to Section 3, inside the switching center, the brains of the operation. Once that radio signal is caught and established, your phone's data is fired deep into the core network. And at the absolute heart of this whole thing is the Mobile Switching Center, or MSC. Think of the MSC as a massive, high-speed digital traffic cop. It's responsible for routing all incoming and outgoing voice calls, authenticating your device's security credentials, managing your handovers as you move from cell to cell, and bridging the gap between the mobile airwaves and the standard public telephone network. But the MSC can't do this all from memory. It relies heavily on two incredibly important databases.
Right, so the MSC relies on the HLR and the VLR. Think of the Home Location Register, or HLR, as the DMV back in your home state. It is your permanent record. It's an essential database holding your secret IMSI, your allowed services, and a pointer to your current location. On the flip side, the Visitor Location Register, the VLR, is temporary. It's a local database tied to the specific MSC where you currently physically are. It only holds your info while you're in its jurisdiction. When your phone pings a new tower, the local VLR tells your global HLR, hey, this person is visiting my area right now, updating your location like signing a local hotel guest book.
And here's a wild stat for you. International standards actually set a strict target bound for all of this. They expect the network to complete a location update or broadcast a page to find your device when a call comes in just 4 seconds or less. 4 seconds!
Which brings us to Section 4, Step-by-Step Call Routing, the invisible handshake in action.
Okay, so we understand the databases now. Let's see how they actually work together in those few seconds before the phone rings. First, let's look at a mobile-originated call. This is when you dial a number. You hit send, your phone sends a call request to the radio antennas, which then passes it to your local MSC. The MSC quickly checks the local VLR database to make sure you have an active account. Then, it uses the Authentication Center to validate your secret IMSI number. The network sends a complex cipher challenge to your phone, and your SIM card uses its burned-in key to solve it. Once you pass that digital handshake, the MSC finally allocates a dedicated voice channel and routes your call out to the destination.
But what about a mobile terminated call? You know, when someone calls you. This is actually way harder because the network literally has to hunt you down. The call hits a gateway MSC, which then interrogates your permanent HLR database. The HLR essentially says, "Oh, I know where they are. Let me ask their local MSC for a temporary routing number," which is known as an MSRN. Once the gateway gets that temporary number, it shoots the call to your local MSC. But remember, your local MSC only knows roughly what area you're in, so it broadcasts a page across all the base station controllers in your area. Your phone hears its name being called, responds to the page, and only then does the MSC open the voice channel and make your phone ring.
So this process works flawlessly if you are standing still. But that brings us to an incredible challenge, and honestly, one of the most mechanically complex engineering feats in modern technology. What on earth happens when you are driving on the highway at 65 miles per hour while talking on this established call?
And that takes us to Section 5, the magic of handoffs, maintaining the connection on the move. To maintain a static phone call in the highly dynamic world of mobility management, your connection obviously can't be glued to just one tower. As you drive, your phone is constantly measuring the received signal strength, or RSS, of the tower it's connected to, as well as the towers coming up on the horizon. When your current signal drops below a specific threshold, it triggers a handoff. If you're just moving around a large building, you might have an intra-cell handoff, simply switching frequencies on the exact same tower. Drive down the street and you trigger an inter-BSC handoff, moving to a new tower, but still under the same local MSC database. But if you drive across the state, you trigger an inter-system handoff, where your call is literally passed mid-sentence from one MSC database to an entirely different one, completely seamlessly. No pressure, right?
This requires some incredibly advanced logic to make cross-country trips work without dropping calls. When you first make a call, the local MSC becomes your anchor. As you drive, it hands you forward to a new MSC. But what if you realize you missed your exit and turn your car around? Well, the network issues a handoff back to prevent what's called the shoelace effect, so the call doesn't loop unnecessarily. And if you just keep driving through multiple cities, the network executes a handoff to a third. This prevents the highly technical trombone effect, where your voice traffic awkwardly winds back and forth across the country through every single tower you passed. Instead, the network intelligently creates a direct, optimized circuit to your newest location in real time.
To summarize the architecture we've covered today, it's amazing to see how the labor of mobile connectivity is cleanly divided. On the left side, you've got the radio station subsystem, handling the raw physics of radio waves and signal strength. In the middle, the network switching subsystem acts as the deep, database-driven core brain, constantly looking up your secret IMSI, routing your calls, and managing those high-speed handoffs. And supporting it all is the operation support subsystem, allowing the operators to monitor traffic and keep the whole network running smoothly.
The sheer scale of this invisible engineering is truly staggering. Thousands of miles of fiber optics, massive databases updating in milliseconds, and hyper-complex radio algorithms all working together silently just so you can hit a green button and say hello. Next time you hear a ringtone, just ask yourself, how many towers, switching centers, and global databases just secretly shook hands in under 4 seconds to reach you? It leaves us to wonder, as we rely more and more on data-heavy applications, what new complexities 5G and beyond will continue to add to this incredible digital handshake. Thanks so much for joining me on this explainer. Keep wondering, keep learning, and I'll catch you next time.